Any physics majors here or physics students? Anybody take a physics class? So every now and then, there's a line in a book that just stays with you. How many of you have heard of random walks? Okay, so the way it's often phrased is you have a drunk, and I know this may be hard for you to imagine as college students, but somebody who is so completely wasted, they have no idea which way is left or right, which way their dorm room is, nothing. And they have a 50-50 chance of walking in either direction at each moment in time. And so the question is, as time evolves, what happens to the drunk? Where does the drunk go? Okay, there's a lot of fun things you can do with this problem. Okay, so in one dimension, the problem is actually very interesting already. This is basically the case of a coin flip. And we're doing the case of a fair drunk, where the drunk has a 50-50 chance of moving to the left or the right, and we want to know, as time passes, where do we expect the drunk to be? So there's a lot of other natural questions you can ask, such as, how likely is it for the drunk to eventually return home? How often does the drunk return home? Does the drunk return home infinitely often? What happens if you do this in 2 dimensions, where now the drunk can move, left, right, forward, and backwards? It turns out in 1 and 2 dimensions, the drunk will still return home infinitely often. In 3 dimensions, the drunk does not always return home infinitely often. And so one of my professors in college said 3 dimensions, that's the reason we live in a 3-dimensional space. It is the lowest integral dimension where the world is interesting for drunks. The drunk actually has a chance of escaping and exploring the rest of the world. If you want to try to do a research project, here's something I would love to do. Imagine a 1-dimensional world where you have a bunch of bars and a bunch of Starbucks. Every time the drunk takes a few steps, the drunk starts to sober up. If the drunk hits a coffee shop, the drunk sobers up a lot faster. If the drunk then hits a bar, the drunk gets drunk faster. What happens to the evolution of the drunk as you start twisting like this? And so again, whenever you see some problem like this, you want to ask, well, what can I do? What kind of twist? How might this be useful? One of the reasons I want to mention physics was when I was a sophomore taking a physics class, they called this the random walk for the drunk staggering home from the lamppost. And the text of the book said, now the primary purpose of physics is not to help drunks staggering home late at night from lampposts. I liked it. This was not the primary purpose of physics. Secondary, tertiary, yes, physicists compare, they care about the behavior of drunks. So we don't really care that much about the behavior of drunks, but we care about systems that can be modeled similarly. So I've already posted, and I'll post it again, some stuff on the stock market. People used to model the stock market basically by a random drunk walk. Now, if the stock market is doing well, you might not have a 50-50 chance of going up or going down. Maybe you have a better than 50% chance of going up, and it's a good market. Maybe we're back in the Great Recession, things are going down. But this was a very popular method, and still is, to model how you think the stock market and prices will evolve over time. There are better approaches, I believe. They require a lot more advanced mathematics, extremely interesting, using fractal geometry by Mandelbrot, Farmer, and their school, and I'll post some stuff on that. But if you've ever seen stuff, a random walk down Wall Street, that's where this is coming from. Unfortunately, the analysis I'm going to give you, I can only make it work very well in the special case when the drunk has a 50-50 chance of moving left or right. For more general probability distribution of P, which isn't that much of a twist, the calculation already becomes more cumbersome than I want to try to get through in class. All right, so random walk. So we'll assume we have 2 n steps. Probability 1/2 go left, 1/2 go right. So if we go going right is +1, going left is -1. And so equivalently, we just need to look at how many heads we have minus the number of tails we have if we flip a fair coin, and that's going to give us our total movement. If it's a positive number, we move to the right. If it's a negative number, we move to the left. Why do you think I want to assume an even number of coin tosses?
So you have the possibility.
Yes, we have a possibility of returning home. So if I assume an even number of tosses, then I can only be 0, plus or minus 2, plus or minus 4, plus or minus 6, plus or minus 8. This is going to be a little bit of an annoyance. But if I had had an odd number of tosses, I could only be at plus or minus 1, plus or minus 3, plus or minus 5. There's going to be this kind of discreteness no matter what. We've already seen issues like this when we used sums of Poisson random variables to try to see a proof of Stirling's formula. All right, so we want to know what is the probability at, how do I do this? We're at 2k. So how would we end up being at 2k after n tosses, after 2n tosses? What must happen? So how would we be at 2k? So how many heads, how many tails? Yes.
It would be 2k heads plus some other variable, and then the tails would be at some other variable.
Okay. Would be that other variable? It wouldn't be the same other variable. How many tosses do I have total? I have 2n tosses. So however many heads I have to have 2n minus the number of heads for tails. Right? So I could have, a system of equations like this. Head plus tails equals 2n. And then heads minus tails equals 2k. And then if I just do some algebra, I should get n plus k and n minus k. And if you look at this, it's easy to see by looking at this that this has to be the right answer. It sums to 2n, and the difference is 2k. So this will give me a motion of 2k units to the right. So whenever you want to do a problem, the first thing you want to do is you want to get a sense of what the scale of the problem should be. How large do you think k is going to be? Do you think it's going to be of size 1, of size log n, n to the 1/4, n to the 1/2, n to the 3/4? About how big do we expect k to be? So we want to know roughly the size of k. Roughly, how big is k? Well, if we had the central limit theorem, that would tell us what's going on, but the whole point is to use this to get at the central limit theorem. What's the poor man's version of the central limit theorem? Chebyshev. So let's use Chebyshev to get some idea of the range of k. And again, the idea is when you're doing problems, you want to have some feel for where the action is happening. All right, so what we have is, let's say xi is plus 1 with probability 1/2, minus 1 with probability 1/2. Our total location is going to be x1 plus x2n. Each is going to be a Bernoulli random variable with probability 1/2. What's the sum of all these Bernoulli random variables? It's going to be binomial with parameters 2n and 1/2. So we know the expected value of x is going to be 2n times p, or n, and the variance of x is going to be 2n p 1 minus p. So it's going to be n halves. So the standard deviation is going to be square root of n over 2, and the mean is going to be n. So now we can use Chebyshev. So what's the probability that x minus n is greater than or equal to k times square root of n over 2? So according to Chebyshev, what's the probability we're more than k standard deviations away from the mean? Yes. 1 over k squared. This works for any k you want. So if we take k that grows with n, the probability is going to become essentially 0. This is wonderful. We don't have to use a very strong version of the central limit theorem or anything like that. You know, the weak Chebyshev is more than enough to handle something like this. Yes?
Why do we get a positive mean?
Oh, good question.
It seems like it should be 0.
You're right, it should be 0, so I've made a mistake here. Oh, you're right, because this is, thank you, I'm mixing up two things. This is not a pure binomial process. What's a pure binomial process? 0 and 1, thank you. So we've now shifted it so that it's -1 and 1, not 0 and 1. So you're absolutely right. So the expected value of this is going to be, let's do it the right way. It's going to be 2n, and then it's going to be 1 times 1/2, thank you, remember to send me an email, plus -1 times 1/2, which is 0. And then down here, we've got to fix it. The variance of the sum is the sum of the variances. So it's going to be 2n. And now for the first, it's going to be 1 minus 0 squared times 1/2 plus -1 minus 0 squared times 1/2, which is going to just be 2n. So that changes the standard deviation ever so slightly. So you are absolutely right that we should have the correct answers here. It's not going to make a difference, fortunately, in what we're doing. This is one of the nice forgiving aspects of mathematics. Because I really don't care about the constant behavior here. The goal here is to sniff out the dependence on n. And really, if it's square root of n, square root of 2n, square root of n over 2, the standard deviation is of size square root of n. That's what matters. Now, when you're doing the actual calculation, you're trying to prove what it converges to, you need to get that constant right. And this could have caused a lot of heartache later, so thank you for speaking up early rather than later. But the key thing here is we see that if we take k to be anything that grows with n, we can make this probability really small. So we could take k equals log n, extremely small. We could take k to be even large, maybe n to the 1/4. Any of these would be suffice to say that without loss of generality, almost all the values of k are going to be, of x are going to be very, very close to 0. How close? Roughly within a square root of n. So the idea is Chebyshev, and unfortunately I guess we're using k in two different ways. The size of x is at most x to the 1/2, I'm sorry, n to the 1/2 plus epsilon for almost all sequences of tosses. Okay? So this is a wonderful benefit from Chebyshev. And again, we don't have the full strength of the central limit theorem, but we now know roughly where to be looking for k. It is extremely unlikely that k is going to be much further away from 0 than a little bit more than square root of n. 5 times square root of n, sure, that's possible. Low probability, but possible. 100 times square root of n, even less likely. But you know, square root of n log n, already that is negligible. Okay, why is this useful? We want to use Stirling's formula. We want to approximate things. If we want to approximate things, we want to know roughly how big quantities are. And this tells us, you know, where we can look at, not just for k, but the more important quantities are n plus k and n minus k are approximately how big. So about how big will those quantities be? They're about size n. What we've just said is k is no more than a little bit more than square root of n with high probability. So we're adding or subtracting a number that's at most of size square root of n. These numbers are going to be of size n. The number of heads and the number of tails are going to be very close to each other. All right, so we get that already from looking at this. What is the probability that x is exactly equal to 2k? So this means we have n plus k heads and n minus k tails. Well, we have a binomial, and we want n plus k of them to be heads, so it's 1/2 to the n plus k, and then the rest are tails to the 2n minus n plus k. This is just, overkill in terms of writing it, trying to make sure I don't make another mistake. This just becomes a 1/2 to the 2n. So it's just 2n, choose n plus k, 1/2 to the 2n, or 2n factorial over n plus k factorial n minus k factorial 1/2 to the 2n. And now all we have to do is look at this as n gets very, very large and see, does this converge to the binomial, so to the Gaussian density. All right. What do you think we're going to use now to do this estimation? Stirling. There's a logical reason why this lecture is immediately following the Stirling lecture, right? And you can see now, here's a nice application of why we want Stirling. If n is large, 2n factorial is going to be well approximated by Stirling. And this stuff down here, these are going to be very close to n. So they will also be large and well approximated by Stirling. This is why it was so important to get a sense of how big k is before we use Stirling. One of the greatest dangers in mathematics is using a result where you do not know it is applicable. Right? We've talked about Binet's formula for the Fibonacci numbers. The Fibonacci numbers are roughly 1/√5 times the golden mean to the nth. This works really well for large Fibonacci numbers. For Fibonacci numbers like 2 or 3, no, because then the 1 plus √5/2 and the 1 minus √5/2, those two factors are not so different that if you raise them to just the first or the second power, they both have a significant role to play. These formulas kick in the limit. So it's very important that both of these are large. So let's just recall Stirling before we use it up the wazoo. All right, Stirling. M factorial is about m to the m, e to the minus m, square root of 2 pi m, 1 plus 1/12m plus ... And we're going to skip the 1/12m and all that stuff later on. That's going to be insignificant relative to the main terms. If you want to do a more careful analysis and just keep track of how much the error term is, you can do that. It's going to be bad enough as is. I have no desire to go to that level. This is more than enough to give you a sense of how the argument works. This will also hopefully give you an appreciation for moment-generating functions. Okay? What I want to do now is I want to work with probably the simplest possible random variable, flipping a fair coin. If we can't even prove the central limit theorem easily in this case, using just standard calculations where we know everything, imagine how much harder it's going to be for other distributions. And hopefully this will motivate why we're spending so much time learning about generating functions. All right, so watch the algebra because there's going to be lots of mistakes. All right, so the probability x equals 2k, this is all in the book. There is no need to write this down. It's going to be 2n to the 2n, e to the negative 2n, square root of 2 pi times 2n. We'll make these squigglies. Now down below, we have n plus k to the n plus k times e to the negative n plus k, square root of 2 pi n plus k. Keep bringing this down, n minus k, n minus k, e to the negative n minus k, bless you, square root of 2 pi n minus k. All right, oh, and we forgot something. We have a 1/2 to the 2n. All right, I feel sorry for the people who are watching this at home because this is really stretching out the video. Fortunately, there's a lot of cancellations, right? So the e to the negative 2n cancels all the stuff down below. What we can do is we can pull out an n from here. We have an n to the 2n. If we pull out an n from here, we get n to the n plus k. We pull out an n from here, we get n to the n minus k. That's an n to the 2n. That cancels up there. We have a 2 to the 2n, a 2 to the 2n, that cancels. Square root of 2 pi, square root of 2 pi cancels. So we're left with the following. We have a square root of 2n from up top and an n plus k and n minus k. All right. Everything else is canceled. We now have a 1 over n plus k. Oh, so we've pulled out an n. So it's 1 plus k over n to the n plus k, 1 minus k over n to the n minus k. All right. As n gets really, really large, remember k is very close to 0. It's at most a little bit more than square root of n. So the denominator looks like n squared. This looks like a 2n. So it should look like 2n divided by n squared, or 2 over square root of n. Square root of 2 over n. All right. K is much less than n. As n gets very, very large, what does 1 plus k over n to the n converge to? It should converge to e to the what? E to the u is the limit as n goes to infinity of 1 plus u over n to the n. Right? So what should this factor go to? I'm sorry? Why e to the k? So because we've got k here, if I look at just this part, that should give me a 1 over e to the k. Now I've got a 1 plus k over n to the k. So we'll have to figure out what that goes to. And then over here, there should be an e to the minus k, a 1 minus k over n to the negative k. There may be a mistake in what I'm doing. Let's see what happens. Square root of 2 over n, the e to the k and the e to the minus k cancel. I can write this as n times k over n. I'll write this as n negative k over n. So e 1 plus k over n to the n, that should be e to the k. And then I multiply by k over n, so I should have a 1 over e to the k squared divided by n. Over here, I get a 1 over e to the negative k. Now k over, so that becomes a positive k squared over n. And so when I put everything together, I should get a square root of 2 over n e to the negative 2 k squared over n. The 2 comes from combining them and taking them from the denominator and flipping it upstairs. The question is this right, or did I just do something illegal? Based on the fact that I'm hopping on I may have done something illegal and I'm constantly waving my hand around this, I probably did something wrong. I did one of the most common mistakes you can do in mathematics. It's very subtle. What mistake did I do? So in a physics or an econ class, it wouldn't be a problem. I'm sorry? Good guess. I think I did avoid dividing by 0, but I interchanged limits. I have a limit of a product is the product of a limits. A limit of a sum is the sum of the limits. When is this true? This is true when both limits exist. You've got to be very, very careful. There's a couple of things in mathematics that are undefined. So undefined are, infinity times 0. We've got to be very careful about stuff like that. And so let's look at the quantity a little bit more closely. So we have 1 plus k over n to the n plus k, 1 minus k over n to the n minus k. And we're saying the limit of a product is the product of the limits. If I didn't have these k's over here, it would be much easier to do the analysis. We said that the analysis of just those terms without the k's was 1. Let's see what would happen. A nice way to notice this is if I could just multiply, I would get 1 minus k squared over n squared to the n. Well, I would want this to be an n squared, so I would do something like this. And what you should be thinking at this point is what I'm doing all seems reasonable, but we've never justified that you can do all this. Where would you justify stuff like this? Real analysis. All right, we have not taken real analysis, so we are not going to try to make anything like that work. But what should you be thinking of as soon as you see this? What should you be thinking? Logs, right? You should always be thinking logs when you see a product. Is there a product here? Hell yes. How many factors do we have here? 2n. There's a huge number of factors here. Lot of multiplication. Okay, whenever you have this much multiplication, think logarithms. And what we're going to do is when we do logarithms, we then Taylor expand. So if we call this quantity p for product, the log of p is going to be n plus k times the log of 1 plus k over n plus n minus k, the log of 1 minus k over n. Okay? And so now we can use logarithms to understand this. So the log of 1 plus u is equal to u minus u squared over 2 plus u cubed over 3 minus dot dot dot. So this is the Taylor expansion for the log of 1 plus u. Here u is going to be k over n, here u will be negative k over n. If you look at what's going on, once we get to the u cubed term, we're going to have a term of size k cubed over n cubed. So the cubed terms, k cubed over n cubed. And roughly, how large could that be? I want to know roughly how big could something like this be? Worst case scenario, how large could k be? No, worst case scenario, how large could k be? Worst possible case. The author of Goldenkrantz and Guildenstern, is that Tom Stoddard? Is that who it was? He's now coming, he's now giving the probability lecture. We're getting nothing but heads. Yeah, it could be as large as n. So n cubed over n cubed could be as large as 1. This would be horrible to Taylor expand at 1. If I'm Taylor expanding at 1, u equals 1, oh dear Lord, I've got an alternating harmonic series. This is going to be very slowly converging. Okay? If k is as large as n, we're in trouble with Taylor series. Do we expect k to be as large as n? No, how large do we expect k to be? About square root of n, maybe a little bit more. Call it square root of n log n to be safe. Or call it n to the 1/2 plus epsilon. Anything like that. We expect this to be bounded by, say, n to the 3/2, if you want, say log of n cubed over n, which is going to be less than or equal to log cubed of n over n to the 3/2. Even when we multiply this by a number as large as n, we'll still have log cubed n over n to the 3/2. So n plus k times k cubed over n cubed will be less than or equal to, say, log cubed n over n to the 1/2 with high probability. And now you can begin to see why we use Chebyshev to get some rough sense of how big k can be. There's a lot of really good stuff in this calculation, which is why I want to go through this slowly. We're going to use this all the time in the rest of the class when we get to the proofs of the central limit theorem, main terms, lower order terms. To some extent, I'm like an accountant at this point, and I only care about the big items. I don't care about the small items. I care about things on the scale of millions of dollars. I don't care about things on the scale of $10, $20. Okay, so here, once I get to the cube terms, it's going to be an insignificant contribution. I can ignore them. Similarly, I can ignore the contributions of the 4th, 5th, 6th, 7th. I only have to worry about the first two. Why the first two? Well, the second term is something of size k squared over n squared. Well, k squared could be as large with high probability as n. So that could be a 1 over n times n. That could be something of size 1. So I do have to worry about the square terms, but I will not have to worry about the cube terms. And again, we will do all of this again when we prove the central limit theorem. So this is a nice way to start seeing some of those calculations. So we get the log of p is approximately n plus k, and now we start expanding the log of 1 plus k over n. So here u is k over n, so we get k over n minus k squared over 2n squared plus dot dot dot. And now we have n minus k, and now we have a minus k over n minus k squared over 2n dot dot dot. Okay? Everybody comfortable here? I'm just doing Taylor series approximations. You know, again, if you see any algebraic errors, it's much better to speak up now rather than later. This lecture is painful enough as is. We don't want to go back and chase things. Okay? So now we just have to start looking. I've got an n times k over n. Ugh, that's potentially as large as k. But I've got a negative n from this part over here. So they will cancel. Yes?
So you need a 2n squared in the denominator?
Oh, yes, that should be an n squared. Thank you. So when we start looking, the piece from this, the n times this cancels with the n times this. The n times negative k over 2n squared, n times negative k squared, they reinforce. So what I'm going to get is I will get a negative k squared over n squared. I had a negative 1/2 here, a negative 1/2 here. It reinforces and becomes a negative 1. That handles the contribution from the two ends. Now we've got to deal with the k. I've got a k squared over n. I've got a negative times negative is a positive k squared over n. Oh, and this is, sorry, this is, because the n cancels one of the n's down there. And I have a k squared over n, a k squared over n, so I get a 2k squared over n. Over here, I'm going to get a k cubed. Here I'll get a negative k cubed, I'll get a positive k cubed. Those will actually cancel. And then, plus much lower order terms. And so when all the dust settles, we get the log of p is equal to k squared over n plus small. So therefore, p is equal to e to the k squared over n times e to the small. And e to the small, if you have a number that's really close to 0, what is that equal to? 1. So we get it's approximately e to the k squared over n. So when n is very, very large, it's e to the k squared over n. Yes?
Why did the sign change?
Over here?
Negative k squared over n to k squared.
From this line to this line? Well, I have a negative k squared over n plus a 2k squared over n. And since this was our factor in the denominator, so since in denominator yields a factor of e to the negative k squared over n. Well, what did we have before? We had e to the negative 2k squared over n. We had the wrong answer. So this argument here is wrong. It seems reasonable, but it's a very common mistake to make. When you have this idea of, well, I know what the limit of 1 plus 1 plus k over n to the n is. Let me just try to play these games. Let me try to play with the exponents. This is a very natural thing to do, but it doesn't work. It can occasionally give you the wrong answer. The only safe way I know to avoid making mistakes is to take logarithms. Taylor expand, and then when you Taylor expand, drop all the terms that go to 0 in the limit, and then exponentiate backwards. Okay? It's a little bit longer. It's much faster to just play the games with the exponents, but playing those games with the exponents can give you the wrong answer. Yes?
So obviously there's like a really small term that's multiplied by the limit in any way doesn't.
Over here?
Yeah.
Yes. That's not going to really matter because this is of size n. This will be of size n plus something of size, square root of n or smaller. And so in the limit, it's not going to matter. This is going to be the main term and will dominate. The reason why we have an error here is we don't just have two terms. We have 2 to the n. We have two n terms. And so small little bits magnify, and they reinforce each other. And that's the problem. OK, so now we can try to finish the calculation. We want to calculate the probability that x equals 2k. Well, we have, it's this expression over here. And now we just substitute. So the factor of square root of 2 over n from before, that was correct. The difficulty, the error was this argument over here. We now put in the correct thing, and it's e to the negative k squared over n. OK. Does this look like a Gaussian, yes or no? Oh, wait a minute, we dropped the square root of 2 pi. Sorry. We had an extra square root of 2 pi, right? Nobody caught that mistake. Right? Because we have two factors of square root of 2 pi from before. So we have an extra 2 pi. Does this look like a Gaussian, yes or no? Give me something that's a plus. Something that says, yeah, this does kind of look like a normal's density. Yeah, it's got a square root of pi, and we know there should be a square root of pi. In fact, this is how I knew I had to have made a mistake. I know the central limit theorem is true. There's no pi on the board. I must have made an algebra mistake somewhere. Whew, there's the algebra mistake. And again, you can see how all the math is connected. The Stirling's formula is giving us, all right, pi is good. OK? What else makes this kind of look like a Gaussian? Yeah, we have e to the negative something squared. Now, we've got to be a little bit careful because we're only working with even numbers. So for us, k has to be even. What's the variance? We saw that the variance was, I think, 2n. So we need to play some games. So the mean is 0. The variance is 2n. And the value is 2k, not k. So really, I shouldn't view this as k squared. I should view this as 1/4 times 2k squared. Because I'm calculating what's the probability x equals 2k. So again, this is now algebraic games. I have to play algebra games to make this look like a Gaussian with the correct mean and the correct variance. The advantage is I know what I'm gunning for. I know which normal it's supposed to be. And we can use that to help us. All right, so k is really 1/2 of 2k. That's how we should really view it. So we get the probability x equals 2k is equal to, the 2's cancel. We have 1 over the square root of pi n e to the negative 2k squared divided by, so I have to put in a 1/4 here, and I've got a 4n. How should I view 4n? 2 times 2n. So we'll have a 1/4 2 pi times 2n, because I wanted 2 pi and I wanted 2n, e to the negative 2k squared over 2 times 2n. Square root of 1/4, 1/2. So I get a 2 up top, square root of 2 pi times 2n, and 2n is the variance, e to the negative 2k minus 0 squared over 2 times 2n. Damn, we are so close. We're only off by a factor of 2. That's not bad. Can anybody save us and fix that factor of 2?
Just the probability that x equals k instead of 2k.
No, I've changed things to 2k everywhere. Where's this final factor of 2 coming from? We are so close.
You could factor out the e to the 1/2 outside of it.
Nope. Where is the factor of 2 coming from? It has to do with the discreteness. So does everybody agree that the bell curve looks something like this? You know, I'm not a great artist, but you know, bell curves I can draw. The bell curve does not look like this. It's not wiggling up, down, up, down, up, down extremely rapidly. What is the probability that x equals 2k plus 1? 0. Because we have a discrete process, the probability of an even number, that's going to be given by this. The probability of an odd number, that's just 0. So really, how should we interpret the probability x equals 2k? We're not going from 2k minus a halves to 2k plus a half. We're actually covering an even number and an odd number. So this too is coming from the discreteness. Okay? It's coming from the fact that the odds have 0 probability. And here's a proof of the central limit theorem for tossing coins. Okay? The purpose of this class was, as I said, to show you why we need to do moment generating functions. You never want to do this again in your life. Okay? If you become a math professor and you teach probability, you have to do this every year. Okay? I did debate just having you guys watch the video and not giving this lecture again, but I think there's a lot of good moments in this lecture that are worth seeing. How do you handle these products? How do you handle them in the right way and not make this mistake? How do you use Stirling's formula? How do you localize and figure out where things are, where the action happens? How do you fix those factors? How do you rewrite the algebra? You know, again, when you know what the answer is, it's a great help. If you've ever done a proof by induction, if you want to find the formula for the sum of the integers or the squares of the integers or the cubes of the integers up to a certain point, if I give you the formula, then you can just crank through the induction. If you have to sniff out the formula, it's a lot harder. Knowing that this is supposed to converge to a Gaussian, I now start to massage it. I start to rewrite things in such a way. I want a 2n because that's the variance. And that's where your comment really helped us now, because if we had the n halves over here, we'd be in trouble. We're evaluating things, the probability that x equals 2k. So even though I see a k squared here, k squared is not the natural quantity. The natural quantity is 2k. So I've got to write k as 1/2 times 2k. Then down here, I want to have a square root of 2 pi. I want to have a square root of 2n. I've got to write it as a 1/4 times all this. And that gives me the extra 2. Okay. So again, lots of calculations here. But at the end of the day, we have a proof of the central limit theorem, assuming we know Stirling. And again, you have to do a little bit more work to make this fully rigorous. You have to handle the lower order terms in the Stirling approximations. We can do that. Okay, this is enough to give you the main brushstrokes. We just need Stirling's formula accurate enough to the next lower order term is of size 1/n. It's much smaller. Okay, it's not worth doing that in class. I've never done that in my life. I've convinced myself if my life depended on it, I could. My life has never depended on it. Okay? Any questions about this before we erase this monstrosity? Okay. If you want a real challenge, try to do this for a biased coin. It's already nice enough, it's already bad enough just with a fair coin. The other thing which I really like about this is it shows you the power of Chebyshev. Chebyshev is weak, but it applies to every distribution. So as long as I have finite variance, I can use Chebyshev. And we use that very effectively here to localize on k. All right, so we've got about 5 minutes left. This is enough time to start chapter 19. Generating functions. So let's let x1 be Poisson with parameter 5. Let's let x2 be Poisson with parameter 7. So if y is Poisson with parameter lambda, this means the probability that y equals m is e to the minus lambda, lambda to the m over m factorial, m greater than or equal to 0, an integer. Let's calculate x equals x1 plus x2. So we've done this before. What method should we use to understand the sum? So what technique do we have to understand sums of random variables? What do we use? We use convolutions. So let's think about what's going on. The probability that x equals k, it's going to be the sum, L goes from 0 to k, of the probability x1 equals L, probability of x2 equals k minus L. So we get a sum, L goes from 0 to k, of the first one is e to the negative 5, 5 to the L divided by L factorial, e to the negative 7. And now we've got 7 to the k minus L over k minus L factorial. And so I wanted to end the day by looking at this calculation, because this fits in beautifully with what we were just doing a moment ago of how do you view algebra. So we've got a sum over L. There are some things that don't depend on L and we can just pull out. We can pull out an e to the negative 5 and e to the negative 7. That gives us an e to the negative 12. As soon as you see an e to the negative 12, what should you be thinking? What does an e to the negative 12 suggest? I'm sorry?
Logs.
I can't hear you.
Logs.
Not logs, although not a bad guess. We have a Poisson random variable with parameter 5 plus a Poisson random variable with parameter 7. We add them up, and we've got an e to the minus 12. What is this suggesting that the sum could be? Could be Poisson with parameter 12. So this is a hint. You want to get to the point where you can look at the algebra and sniff out what to do next and what the answer could be. Seeing a negative 12, I start to think maybe it's a Poisson. I have a sum, L goes from 0 to k. I have an L factorial and a k minus L factorial, a 5 to the L, a 7 to the k minus L. I'm deliberately writing it like this because this looks so much like an expression we've seen before. It's missing just a little bit. But what does this look like? L factorial, k minus L factorial. I'm sorry? It looks a lot like k choose L. So let's just put in a k factorial here. That's okay to do, right? No, we can't just put in a k factorial. But if I divide by k factorial, no problem. All right? We divide by k factorial. And since k has no L dependence, I can put that outside the sum. This is the binomial theorem. This is just going to be 5 plus 7 to the kth power. So I get this is equal to e to the negative 12 over k factorial 5 plus 7 to the k. Well, 5 plus 7 to the k is more commonly known as 12. So we get e to the minus 12 times 12 to the k over k factorial. So what we've just shown is the sum of two Poissons is a Poisson if the parameters are 5 and 7. There was nothing special about 5 and 7. I could replace it with lambda 1, lambda 2, and the argument would follow similarly. So here's a nice proof that sums of Poisson is Poisson. You can see the convolution playing the key role here. And you can see the difficulty was how to view the algebra. This is very similar to one of the homework problems we had. Remember, we had a homework problem where you were flipping some coins. The number of coins you tossed was a Poisson random variable. And then you flip that number of coins and you want to know what was the distribution of the number of heads. And it turned out that that was a Poisson random variable. It's how do you sniff out the algebra? How do you see how to analyze it? This is the difference between probability and statistics. It's getting these closed form expressions. What we're going to see is we're going to see a way to automate this. And that's going to be through the convolutions and moment generating functions. Moment generating functions are built in such a way that they have convolutions defined as part of their being. And they will do all this algebra for you instinctively. The way I like to view this, and we'll end on this note, is if I give you a quadratic and your life depended on it, could you find the roots? What could you do? Quadratic formula. Now if I give you x squared minus 4x, let's do 5x plus 6. What are the roots? All right, so I hear x minus 2, x minus 3. How many of you use the quadratic formula to solve that? I hope you're scratching your hair and not saying, okay. Okay. If you use the quadratic formula to solve this, see me, you've got issues. Right? For something like this, you can just look at it and see the answer because you've done enough of these problems. But if that fails, there's a mechanical procedure you can use. That's how you should view all of this stuff. Over here, a lot of this is inspiration right now. The goal is to do enough of these so it's no longer inspiration so that you have a way to approach this. And then for the other ones, to have a mechanical procedure to generating functions. All right, we will continue on Wednesday.